Should I stop sharing?
No, you should start. You should be sharing. You should be sharing. And I see it. Okay, I want to welcome everyone. My name is John Derry. I'm with the CGIA. I'm the moderator for the session entitled USGS Elevation-derived Hydro Specifications and Capture Conditions. We have one speaker today, Sylvia Terziati, who I've known for many years. She is the USGS National Map Geospatial Liaison for North and South Carolina. She splits her time between the water mission area and the National Geospatial Program in USGS. Her recent work is focused on evaluating LIDAR-derived products and whether they meet the national specifications. Her master's is in urban and regional planning from Virginia Commonwealth University. Anthony, please send in your questions via chat and they will be answered at the end of the presentation. All right, Sylvia, take it away.
Okay, I'm gonna hopefully make it big. I'm gonna go ahead and turn off my video real quick, just to avoid overtaxing my computer. Thanks for having me. Like John said, this is a short talk about the elevation-derived hydrography specifications that we've put together recently at USGS. And let's see if I can get it to advance. Yes. And I am the Associate National Map Liaison for North and South Carolina, but as John said, also I do work at the water mission or for the water mission area also. So I've been involved with hydrography and generating elevation-derived hydrography for a long time. So it's near and dear to my heart. I also want to recognize Christiane Archuleta, who is my co-author and has been working with me on the research for this project. And she is out of Rolla, Missouri, and in the National Geospatial Technical Operations Center, NGTOC. So the USGS is currently working toward producing better aligned hydrography and elevation products by creating a system to acquire elevation-derived hydrography, also referred to as EDH, and that's probably what I will refer to it as. It is horizontally and vertically integrated with the 3-depth bare earth digital elevation models and also aligns with National Hydrography Dataset requirements. So the three main products that EDH can be used for are as break lines to hydroflatten digital elevation models, processing for pre-conflation of features to the National Hydrography Dataset, the NHD, and hydro enforcement of digital elevation models. And in order to meet the vision of the USGS for well-integrated elevation and hydrography data, we recently published 2 new specification documents. These new documents connect the dots between existing LIDAR and NHD data, and they are the elevation-derived hydrography acquisition specifications and what we call the READ rules: representation, extraction, attribution, and delineation. So now I'll just jump into what is actually in the specifications. This table shows what is covered within the first document, the acquisition specifications. First, I do want to stress that the specs don't tell a user how to create the hydrographic features, but it describes what requirements need to be satisfied in order for the finished hydrography data to be submitted to the USGS as an elevation-derived hydrography deliverable. The specifications help the USGS acquire data that is consistent attribution and is compatible with NHD, and it meets a minimum required collection criteria and meets horizontal and vertical positional requirements. These tables kind of describe the types of features that we're looking at. In the table on the right, you can see the types of features recommended for collection. The list of features includes those that can be derived from elevation data and correspond to NHD-F codes or LiDAR-based specifications. The NHD features that you wouldn't see on this list are ones that would be too difficult to derive from an elevation data source. EDH coding also allows for the collection of various types of hydrography data that can be used for different purposes. The F codes and NHD F codes are defined in the same way. And as in the NHD, they facilitate, so because they're defined the same way as the NHD, they facilitate the conflation of EDH to the NHD. The coding system allows for the collection of features outside of these specifications as well. Users can add their own codes that can be tracked outside of the NHD, or additional NHD codes that weren't included in the EDH specifications can also be included with that user-defined code. The other important thing is that we want to help integrate the hydrography into the elevation data set. And so the coding provides the ability to use the features as elevation break lines. And these meet the LiDAR-based specification break line requirements for hydroflattening. The features listed in the lower middle table are those needed for hydroflattening a DEM surface to meet the LiDAR-based specification. There are also codes that can be used for hydro enforcement. For instance, you could use the codes to find culverts to hydro enforce a DEM. And if your LiDAR project collects EDH data, the data can be used both as break lines for elevation purposes such as hydroflattening and for conflation into the NHD and for other purposes that meet user needs outside of the USGS. For elevation-derived hydrography, there's a minimum set of features required for collection. Although as stated before, people can collect additional features outside this baseline collection set. The minimum set of features is comparable to the density of what's currently in the NHD dataset. Although we use the NHD as a baseline set of features, the feature alignment must match the bare earth, 3-depth, DEM horizontally and vertically, and a z-value is required on every vertex. Features that are no longer present in the LiDAR surface must be removed, and features that meet the read rules that were not present in the NHD should be added. To try and avoid overmapping, which is common using LiDAR-derived elevation sources, additional features above the minimum set of features must also meet these requirements. A feature must be visible on the DEM, or if it's not visible on the DEM, it should be present in accepted ancillary data sources, or it can be collected if it's necessary to connect the hydrologic network. And in this example, the yellow lines would be the additional features added to the baseline geometrically corrected NHD features in red, and recognizing that additional line work will be added that may not be a verified stream channel. There's also a code that's being introduced, which is the drainage way code, to allow for features that may need verification later. For our alignment requirements, all features must align with the DEM and with the current NHD where appropriate. Although we do not want correctly placed EDH geometry moved to snap to incorrectly placed older NHD features. But all features must have a downstream orientation, and they must match between project areas and be logically and spatially consistent within the elevation data, both horizontally and vertically. So now we'll just briefly describe the companion document to the specifications, the read rules. The read rules describe in detail all of the features that are to be collected and the parameters for collection. The document's designed so each feature type can be separated as a whole from the rest of the document and used by a technician who's working on a specific feature type. So if you have someone who's working on stream rivers or artificial paths, they can take that section from the document and have all of the information they need for that collection. We also have online resources, a website that we're developing. The website, you can access the specification documents and also additional resources, such as an example of errors that can be encountered while producing EDH. Here's an example of one of the error explanations. This one is for determining the correct length of a connector feature through a dam between a water body and a stream. Now I'm just going to give a quick overview of our inspection process and some of the tools we've developed to evaluate the accuracy of elevation-derived hydrography products. So now that the USGS has specifications for acquisition, we've begun some pilot projects to explore collecting hydrography data from elevation data, storing it in the EDH format, and converting it to NHD data. So this requires a robust inspection process, complete with tools to ensure the best possible data is available for NHD and for use as break lines for elevation derivatives. Our current pilot is in the Kobuk River region of Alaska, and our research is currently developing the EDH inspection process and inspection tools for automation. As part of the implementation research, we're trying to not only provide assessment data to inform our inspection process, but we're trying to provide meaningful feedback to the contractors so they can improve their collection process as well. So the inspection process looks at three basic categories: completeness, integrity, and placement. So we check that all the features that should be there are there. We check the correct codes that are used for the correct types of hydrography, and that the features are placed in the correct location, both horizontally and vertically. So for the completeness category, we have several things to consider. Have all the previously collected NHD features been captured? And if so, are they correctly positioned? And do they follow the current specifications? Have all the additional features not present in the NHD, which meet the specifications, been added? And have features been removed which shouldn't be there? And have we increased the density of features appropriately for the resolution of the source data? In this example on the left are the original NHD lines adjusted to match the elevation surface, and the figure on the right shows the increased density of features. So features that meet the specification and are not included would be considered an omission error. For the data integrity category, we check to make sure the features are being collected according to the coding specifications. In some cases, such as culverts, there are specific rules describing how the codes should be applied based on characteristics of the feature. And our integrity tests check to make sure the rules are followed appropriately. And our final category for evaluation is horizontal and vertical placement. This probably takes about 90% of our time. For horizontal placement, we look at the integration of the drainage network with the elevation surface by examining the geometry. In this example, you can see a number of places where the drainage lines were not placed properly in their channels. Somewhat easily seen with visual inspections, but we rely on tools to generate flags to guide us to where the problems might be. And we also look at the vertical alignment between hydrography features and the DEM. In the left of the image, you can see several blue streamlines, two of which are intersected by a yellow cross-section line. In the graph below and to the right, you can see two blue points, which represent the intersection of the stream with the surface, both of which are within 1 meter below the surface of the DEM. So this will be appropriately placed. The other vertical placement test that we consider is how the drainage network flows across the terrain. So Z values should be monotonic. In other words, the Z values should be lower or equal to the preceding value in a downhill direction. And in this example above the graph, you can see the stream highlighted in yellow. And in the graph, you can see that the stream is monotonic and that the profile points are flowing in the downstream direction. And each dot on the graph, you can see the yellow dots represent a vertex on that stream. So tools are also being developed using the Alaska IFSAR EDH pilot project data and in a pilot project area in Southeast Texas where we're using LIDAR. The tools are currently developed to look at feature density, horizontal and vertical placement, and topology issues. We're also doing additional research to develop new tools to evaluate horizontal placement of streams within channels, evaluating methods to predict the probable channel locations, to evaluate proprietary drainage network delineation algorithms that were developed by contractors that we're working with, so we can compare their stream location placement against the various predicted paths. To do this, we're evaluating the use of geomorphological indicators such as geomorphon values and depressions, D-infinity flow models, openness and plan curvature. And additionally, we're looking at D8 flow paths and the impact of low slope areas and sinks. And contours and profiles are also being used for other, to find other misaligned features. And now just a couple of examples of the EDH products and how they are used for elevation derivatives and NHD production. Increases of density is one of the things that we see. We are getting about, in Alaska, we're asking for about 2 times the number of features, and we're getting much better alignment with the elevation surface in the EDH compared to the NHD. In these examples, pink lines or magenta lines are the original NHD and the blue lines are the EDH features. So you can see quite a few more features are present. And then we're also seeing a lot of improvement as the contractors are going through the process and learning to derive these streams because of the diagnostics used, and starting with a 100% inspection process, we were able to pinpoint areas with issues and flag them so that contractors can resubmit their work so it better integrates with the DEM surface. These 2 images are examples of the updates to a delivery area between the first and second submission. Red lines are the first submission and blue are the second. Improvements in density, horizontal placement, and vertical placement are seen. And the yellow areas in the background are the areas we've identified as probable channel areas using our tools. And updates are also being made to the watershed boundary data set to the HUC 12 level. The EDH is used to define pour points and the DTM is used to refine the ridges. In these examples, the red line is the existing WBD and the black line is the updated WBD. And as mentioned before, a primary goal of the specifications is the integration of elevation and hydrography data. So coding and defining special cases and features are specifically defined to meet this goal. In this example, the E class or elevation class of 1 is used to identify any water body that should be used for hydroflattening, and or can be imported from the LiDAR source from if it already exists to use to integrate within the EDH. Most EDH features characterize water in a well-defined drainage network, but in less defined areas, there may be barriers to flow or difficult to detect channel areas on the DEM surface, and indefinite surface and subsurface flow features can be used to traverse these areas. The most common type of indefinite subsurface connection is a culvert. The specification document has detailed instructions and figures to help users identify culverts and place them correctly within the EDH network so that they're spatially integrated with the elevation surface. And another type of indefinite subsurface connection is the underground conduit, which should be used for natural underground drainage paths or to breach other types of features that naturally block the flow, such as landslides, moraines, glacial till, or other naturally occurring berms. This is a common usage in karst terrain. Also, the pre-conflation processes are being developed to transfer existing F codes to the new line work collected through EDH. And this is going to be automated based on conflation feature reach codes. Other features collected for EDH that are not in the NHD, which the only feature type right now is the culvert, is going to be converted to an NHD event at the time of conflation. So in summary, our goal is to eventually provide funding for EDH. However, unfortunately, we don't have a mechanism at this time to do so, but we're working on a call for action that will outline the steps and resources needed for the 3D national terrain model, including EDH partnerships. The targets to complete the plan by early spring 2021, may go into summer, I think. We're doing research on how to make the NHD conflation process easier, faster, and more scalable so it works better with the EDH data. And so far it's been pretty successful. We're working closely with NSGIC to provide resources and guidance to states that are interested in creating EDH. And we're very interested in talking with our NHD stewards and partners about their interest in updating NHD with EDH data and learning more about their plans in the process. So that is all I have. So any questions or feedback, I'll be happy to try and answer.
Sylvia, thanks. That was very informative. I personally am looking forward to this being developed in North Carolina. We have a question from the chat is, what is the difference between the terms hydrography and hydrology?
Hydrography is the map feature, the feature on the cartographic feature or spatial feature that represents us hydrology feature. Hydrology is more of the science behind it.
Okay, thank you. And I said before we got online, how will EDH be integrated in NHD? And it sounds like there is a plan.
Yes.
That's being tested.
Yes, and I mean, it's not too difficult just conceptually from the way that we've incorporated new versions of line work into NHD in the past, except for now with the EDH framework, our tools can be streamlined to look at the fields and the the accuracies of the line work, knowing what is basically coming into NHD, so can be enhanced so it works really pretty seamlessly to go from the EDH product, which has all the topology rules and everything that NHD already needs. So it's fairly seamless to get into the NHD.
Great. Another question is, has 3DEP online web app been updated with the recent 2014-2017 QL1, QL2 LiDAR?
Oh, goodness. I wish I could say yes. I don't believe it has. I believe you can get the source data, but not the USGS 1 meter standard product that they create. We have all of the data because we partnered with the state to collect a lot of that data. I think all but one of the phases. So we do have all that data. There were some issues with it being Geiger mode LiDAR, which didn't really fit some of our requirements for the data. I think those were worked out. I think it's just a matter of there's just such a backup of data that's we're still trying to get into our system. I apologize for that. I hate to see that big blank spot when I look at those maps. And now we're getting new LiDAR data, so that'll probably be in there before the phase 4 and 5 are.
Right. I have another question. Where can I find more info regarding the nationwide LiDAR data collection?
You can go to USGS. If you look under, well, probably the easiest thing to do is to Google USGS 3DEP program. And that's the number 3 DEP, or that will, or 3D elevation program, that will bring you to the program project sites, and it should have all the background and links to where to download data, how to access the specifications for the LiDAR data, and pretty much everything you need to know about it. There's also a new video I just saw that just there's a video series that USGS puts out about the easy ways to access the data and download the data. Those are a little bit hard to find, but if you search for the USGS YouTube site with 3DEP, you'll also find a lot of resources there. And the same with NHD.
I think that was the last question, Sylvia.
Okay.
Yeah, I've been coming up on the hour. So thank you very much. And there's another session starting at noon. Thank you all for attending.
Great.